So I wanted to just look at a quick example problem from chapter 5 that would be showing you how we calculate the reactions that we have at the supports. So basically what we're learning about when we think of these supports that are introduced in chapter 5 is it's an expansion, in a sense, on the normal force. In this context, when we put a book, say, on a table, we know that the table will exert a normal force on the book. That normal force is named actually because it's perpendicular to the plane of the table and it acts up. It's supporting the book. Well, now in the pictures that, in the scenarios that we look at in mechanics and statics, the idea of supports is a little bit more complex because we have different scenarios where there can be some sort of support offered. For instance, in this picture here, the truss, right here is a pin. That pin is actually offering a support, and it's in the form of reaction, which if we circle back to the normal force, it also is a reaction to the force of gravity pushing down. But here the pin is exerting a reaction and a support, but it's acting in two different directions. Now the way that we can figure out the direction of a support is thinking about which kind of motion does it prevent. Because of the pin right here at point A, those beams cannot move in the x direction and they cannot move in the y direction. So the support forces that we deal with are going to be in both the x and the y direction. Now, the support at point B is a little bit different. You can notice it's not a pin, and it's just like this little like curvy shape, almost like a ball, but like a semicircle. Now, if you think about it, at that place where that semicircular support is touching the flat concrete, it actually could move from side to side. There's nothing about that shape that prevents it from moving in the x direction, but it does prevent motion in the y direction. And so the support reaction at B is totally vertical. So the way that we can then calculate these support reactions once we label them is we apply the conditions of equilibrium, which is the overall topic of chapter 5, which is equilibrium. It's just that now we have to be more sophisticated, and so we have to be aware that these supports exist, and we have to put them into the problem in order to properly analyze what's going on. Okay, so if I go to point A, right here, I have, it's a little offset, but I have a support reaction AY that's vertical and a support reaction AX, and I'm going to draw it to the right. I choose not to really spend a lot of time thinking about the direction of my support reactions. If I get the wrong direction, my answer will just turn out to be negative, and then I know it's in the opposite direction. So it's just not, to me, worth spending a lot of time worrying about. And now for B, we said was just totally vertical. And so that is how I'm going to label these reactions in this, for this truss. This is actually called a truss. Now, you might notice, I want to like clue you into something. You might notice that when you look at pictures, typically, there'll be a pin at one end and then some sort of smooth support like we see at B at the other end. The reason for that is math makes it have to be that way. We have three conditions of equilibrium. Forces in the x direction equal 0, forces in the y direction equal 0, and then moments about any point are 0. Mathematically, because I only have three equations that I can apply in this 2D problem to equilibrium, I can only have three unknowns. So I couldn't put a pin at B because then I would have a BX and a BY. I'd have too many unknowns. So I'm going to first apply conditions of equilibrium. The sum of the forces in the x direction are 0. I have AX plus F1 equals 0. AX is equal to minus F1, which is equal to minus 6 kilonewtons. Here's the values for the three forces there. So right away I put AX in the wrong direction. I don't care because it doesn't matter. Now I know that it's pointed to the left, and maybe I would have been smarter to draw it to the left in the beginning, because from the picture I should have seen that that was true. But I wanted to show you that it really wouldn't matter in the long run if I chose the wrong direction. You might remember similarly there are scenarios like this that we encountered in general physics, where choosing the wrong direction would just give you a negative value and it was all good. Now, let's look at forces in the y direction. I have AY minus F2 minus F3 plus B. So that means that AY plus B is equal to F2 plus F3, which is equal to 7 plus 9, which is equal to 16 kilonewtons. So AY plus B is equal to 17 kilonewtons. Now clearly, I don't know what the two forces are individually, I just know what they add up to be. Using the sum of the moments about any point on this truss and saying that it's equal to 0 is my last condition of equilibrium, and that's the one that's going to allow me to figure out which is which. So when you're choosing a moment, a point about which to find the moment for this equilibrium condition, you can choose any point on the object. So I could have chosen any point on that truss, but some points are better than others. The best thing for me to do is to choose a point where some forces go through that I don't know, because then they will be eliminated in this equation. For instance, when I chose point A, I know AY and AX both pass through point A, therefore they can't produce any moment about that point. And so I thought that was a great place to choose. So when I do this, then I like to start at my pivot point, which I chose as point A, and move from left to right. And as I do that, I'm going to write expressions for the moments that the forces produce, that the forces I encounter, what they produce. So F1 is up here, and it's to the right. If I think about pushing that way, that's going to tend to cause a clockwise rotation, so that's a negative. The distance from point A to the line of action of F1 is 2 meters. All right, so the other one is F3. That one's also going to cause a clockwise rotation, so it's minus F3. And that one's also 2 meters away. Then I have that's F2, silly me. F3 is 4 meters away. It has the same sense as F2, so it is also going to cause a clockwise rotation. And finally, we get to B. B is in the opposite direction. If I pull up, I'm going to cause a counterclockwise rotation, and that is 6 meters away from point A. So if I put in my values of minus 6 times 2, minus 7 times 2, minus 9 times 4, plus 6b. If I add all these together, I find that 6b is equal to 62. So b ends up to be 10.3. Oh, sorry, that's kilonewtons. And once I know that, A is going to be 17 minus 10.3 kilonewtons. And that ends up giving me, why did I write 17 here? It was 60, sorry. And this ends up to be 5.7 kilonewtons. All right, little mistake I made along the way, but I fixed it. It's 16. All right, so that's the idea of how we find these reaction forces. I think you're going to get used to the supports as you use them. And again, I think the easiest way to remember what kind of forces they will offer is thinking about what kind of motion that they prevent.